All right, this is a recording for Wednesday, September 8th of 2021 for honors physics. We had started a discussion on position, displacement, and distance traveled during our class period today. Unfortunately, we had a slightly abbreviated schedule and did not get as far as we would have hoped. So I'm going to walk you through what we did do, and then tomorrow we'll pick up from that point and move on. So there's two things that you'll need for this lesson. The first thing is the student note sheet, which is on Canvas. And the second is the PowerPoint, the Google slideshow for the lesson. So if you'll take a moment, pause the video here and bring up both of those items, that would be super awesome. So again, you need two things from Canvas: the student note sheet and and if you want, you can also pull up the slideshow, or you can watch, of course, I'm going to be playing it. So whatever works for you. Excuse me, I did not print the slideshow for students. I gave the note sheet as a way of you recording the information that's essential from this presentation, along with the practice that I think you need as you're going into this. Okay, so again, we're going to talk about position, displacement, and distance travel. Oops. So I did go over a couple of things just for housekeeping purposes. The county has asked us to provide methods for students to monitor their own academic growth through each unit. And so that means that we're going to be giving, in general, pre and post unit assessments so that you can kind of see what do you know, what do you not know, and then how that knowledge has changed throughout instruction. Each unit will have some instruction and practice, a formative check. Those are like quizzes or similar checkpoints, and lab activities. Then, of course, we'll have a review and a post-assessment so that you can see where you are, what questions you may still have, and what you need to practice more on before you take our summative, which is like a unit test. So as we move on past this first unit, you'll see this pre-assessment and post-assessment more on the unit level. Since this came to us right as the school was beginning, we did not change our first unit. And so our first unit of instruction, you'll see more of a pre-assessment and post-assessment of some form on each lesson, where we're sort of saying, okay, what do you know? And then at the end, we're saying, let's look at how that knowledge has changed and or solidified and what questions you might have. So we ignored this. We decided not to do a separate pre-assessment. And so we'll just use the warm-up from this activity to do the pre-assessment. I think I jumped past a slide. Bear with me 1 second. Oops. Oh, okay, the agenda's afterwards, sorry. So our mastery objectives for today, we have two of them. By the end of the period, you should be able to analyze position versus time graphs for objects moving in one dimension, and you should be able to apply graphed information to describe the motion of an object in terms of its position, displacement, and total distance traveled. We didn't quite get to these mastery objectives in our lesson today. We started working on our definitions and the background knowledge and foundations that we need to do this. So we'll really look at completing these mastery objectives tomorrow in class. So our pre-assessment in this unit will be our warm-up. Then we're going to talk about describing directions, vocabulary of motion. And we started to talk about motion maps, which are a method of modeling or illustrating motion, but we didn't quite get to the graph. So we'll pick up on that tomorrow. I did take this graph matching activity and move it forward a little bit because we did not get through today's lesson. So a reminder for your homework, the things that you should have submitted by now: the Who I Am sheet, and remember that's not graded, but that was helpful for me to kind of better get to know you. The measurement interactive, there was no grade to that, but I want to give you some feedback, so please hit that submit button. The county safety test, no grade, but you have to have 100% according to the county. So you need to make sure that if you haven't gotten that 100%, go back and do it until you've reached that 100%. If you need help, please let me know. We're holding off on these science safety contracts because you did not receive a printed copy yet. You will receive that tomorrow during class. And then you had a metric conversion activity from last Friday that you were working on, and that's due today at midnight. So Wednesday at midnight. If you need more time, please at least get started on it, right? And then let me know what's going on so we can work with you on a revised timeline for submission. The PA graph matching, again, we did not assign that for homework today. We said, hey, things have been a little bit crazy. So let's, with today, we didn't get as far as we wanted. So let's hold off on this and we'll do this. We'll move this to part of what we look at tomorrow. It's due Friday at midnight. I don't really see a problem with that due date, but if we need to adjust it, we'll adjust it tomorrow. Okay, so we got started today with sort of a pre-assessment / warm-up, and it says you and a friend are at the United States Capitol. That's the blue star in the bottom right corner of your screen. Your friend is new to DC and wants to see the White House, which is over here at this red star. How would you explain to him how to get there? So I'm going to ask you to pause this video and take a moment to write out the directions for your friend, okay? And you'll see a space on here on your note sheet for that to happen, for you to put your answers. You can print a copy or make a copy into your file and or pick up a copy of this from me in the classroom. I do want to point out that I have put the homework up here, but a reminder that we're kind of not starting that necessarily tonight, okay? So pause the video, take a few minutes and do the warm-up. So common things were starting here at the Capitol and maybe taking Pennsylvania Avenue down to the White House. Some great comments about making sure you understand that at Freedom Plaza, Pennsylvania Avenue doesn't cut through there. So you really do need to give directions on how to get around that plaza in order to get to the location. Better descriptions from here were to take the start at the Peace Monument, take Pennsylvania Avenue northwest until you reach Freedom Plaza, and either go on East Street northwest until you get to 14th. So that kind of continues, right? Or you can at Pennsylvania Avenue at Freedom Plaza, you can make a right on 13th and go up to East Street northwest and make a left. So either way, if you continue on to East Street or you make a right on 13th and then a left on East Street, you're going to be getting onto 14th Street so that you're headed, here you're headed on 14th Street, so you're headed towards Pennsylvania Avenue. When you pick Pennsylvania Avenue up, you'll go back, you'll continue on until you get to Hamilton Place. Hamilton Place. Okay, some other things we had some students say, take First Street until you get up to East Street Northwest and go across until you hit Pennsylvania Avenue, follow that up. We had some other students say take Constitution Avenue, which is north of the Capitol, take Constitution Avenue west until you get to 17th Street Northwest, make a right and take 17th Street Northwest, north until you get to State Place, and make a right into State Place, and that's where the White House is. The most important thing here is that you are careful about your directions. So for example, I couldn't say, leave the Capitol and make a right onto First Street. Well, that would depend on, I'm sorry, right onto Constitution Avenue. That would depend on where we got out, right? And actually that doesn't work at all. So if any place here, if I make a right, I'd be going the wrong direction. Make a left, right? I could say make a left. But there's other areas. I'm trying to find that intersection I was talking about. Like Constitution and Pennsylvania, I have to tell my friend to go northwest on Pennsylvania Avenue. If I wasn't careful about the turns, they could end up in the wrong location. So you want a direction, and preferably you want a measurement, whether it be how many blocks or how many miles. It's really difficult to do with this particular map because it doesn't have a scale. But that's what we were looking for, is that your directions were specific, that we didn't say things like, go to the Capitol and go up to the White House. It's on Pennsylvania Avenue. Like that would be really confusing for people. All right. So when we describe motion in physics, we want to clearly communicate the location of an object in space. In order to do this, we need a reference point, what we call an origin or frame of reference that we're going to look at. And from that reference point or origin, we give you a distance and a direction, and that points you to where we're headed. So an origin, again, is the position of reference by which we measure all other, point of reference by which we measure all positions. And usually this is a 0 point on our graph. So if we go back to our note sheet here, you're given that illustration, you're given 3 questions. What is an origin? Where is it in this image? Which building, cafeteria, dorm, physics, library, which building represents the origin in this image? And when you graph data, where would the origin be? So pause for a moment to complete your note sheet. I'm going to put the definition back up. So again, that first question, our definition is the point of reference. An origin is a point of reference by which we measure all positions. And this is what we consider our 0 point on the graph. In this illustration, our 0 on our number line is at our dorm. So our dorm is the origin in this example. We can put that origin wherever it is convenient for us. We make that decision. We just do need to let everybody kind of know where we're going to be starting. Lastly, what does the origin look like on a graph? Well, the origin on the graph is usually the intersection of your horizontal and vertical axes. It's that 0 mark on your axes, right? So the 0 on your horizontal or x-axis and the 0 on your vertical or y-axis, and we generally make that on a graph be where they intersect. All right, so again, on our next section of the note sheet, we're going to look at some definitions. So distance is the amount of physical space covered along a path taken between 2 locations. How far are you traveling as you go along your route? That depends, right? Some routes are shorter than others as we go between 2 places. Distance can be measured in any unit of length, feet, meters, kilometers, miles, inches, anything that's appropriate to the scale of what we're measuring. We talked about that last week in our measurement labs. We'll commonly measure in metric units of meters for our length. And the meter is abbreviated with a lowercase m. It's important that it's a lowercase m, not a capital M. Position is the location given by a distance and a direction of an object at some point in time relative to the origin or frame of reference. When reporting a position, we will have a length measurement accompanied by a direction, which is all relative to our origin or our frame of reference. So let's go back and look at that note sheet and make sure that we can fill this in. I'm going to put the two definitions up again. We're going to fill in number 1 and number 2. I suggest you pause for a moment and take a look at those. I'm going to put this up again for you so you can see the definitions. You're filling in 1 and 2 where it says definitions. Okay, so let's come back to that note sheet. And number 1, distance. Distance is the amount of physical space covered along a path taken between two locations. What is your path length? How far are you traveling as you go from one location to another? It can be measured in any unit of length, example, feet, meters, kilometers, miles, etc. The unit we will most frequently use, because it is the base unit for length in the metric system, is the meter. And the meter, M-E-T-E-R. The abbreviation for this unit is a lowercase m. So let's give an example of a distance. So if I travel from A to B, from the tree to the house, I go 4 meters. If I travel from the small tree to the large tree to C, from location A to C, I have 2 paths I can take. I can take a straight line path, which is 5 meters long, or I can go to the house and then I can go to the tree, which would take me 7 meters. So that's a distance. Notice I'm not telling you which direction I'm going or anything. I'm just telling you a measurement of length. So let's say that we want to look at, okay, let's define the next one. Number 2, position. Position is the location, distance, and direction of an object at some point in time relative to the origin or frame of reference. The position is going to require a numerical value of the length measurement. Of course, it has to have its units, and a direction that you're traveling relative to the origin or frame of reference. So let's look at an example here. So the position of the tree, let's let the little boy at the small tree, location A, be our origin. We can stick it any place. The position of the house is 4 meters, a little east of north. I don't really know what that angle is, okay, but it's north is straight up, so it's a little bit east of that. So 4 meters, it's not really northeast, but a little east of our north direction. And the large tree is 5 meters, and that's fairly close to northeast. That looks almost 45 degrees, maybe a little bit smaller. Okay, so we're giving our locations. If we were to look at C, for our origin, then our house is 3 meters west of the large tree, and the little boy is 5 meters almost southwest of the tree. So that's what we mean by a position. We pick some origin and we're saying, here's where we are relative to that location. Okay. So now let's look at our next vocabulary term. And our next vocabulary term is displacement. So displacement is the change in position of an object from its starting location. So when we report a displacement, we report a length and a direction relative to the starting location. So let's go back here and look at our note sheet again. And here on number 3, we're asked to fill in that term. That term is displacement. Displacement is the change in position of an object from its starting location. It is truly a measurement of the straight line length between the starting location and the ending location of the object. The length must be reported with an appropriate unit of measurement and a direction relative to the origin or frame of reference, okay? So before we get to the little practice exercise, I want to do a little practice here. So bear with me. Okay, so let's take a look at this image that we were working with before. Let me make it larger. We start at the dorm. Let's travel to the physics building and then from the physics building to the cafeteria. Take a look at that route from the dorm to the physics building to the cafeteria. What is our total distance traveled as we go from the dorm to the physics building to the cafeteria? You can pause the video if you need a minute to think. Okay, let's work it out together. So we go from the dorm to the physics building, that's 2 blocks. We go, remember, we don't care about the direction, we're talking about distance, total distance travel, 2 blocks. Then we're coming back to the dorm, right? Because we've got to get to the cafeteria, we're going to pass the dorm again. So we go another 2 blocks in to get to the dorm, and then we go another block further. So we have 2 plus 2 plus 1, that gives us a total of 5 blocks. That's our total distance traveled. Now let's think for a moment our displacement. Once we finish that route. What is our displacement once we're at the cafeteria? Remember, our frame of reference is that dorm. Pause the video if you need more time. So you should be able to see that I am 1 block west or to the left of the dorm. That's my displacement, 1 block west of the dorm. Okay, so here's a great time to pause the video and answer these questions on your note sheet. I'll go over them in a minute. It says, after getting hit, a baseball player runs from home, the blue star, to the first base, red star, to the second base, yellow star. What do the stars represent? That's a multiple choice question. What do the arrows represent? What is the total distance? This is again a multiple choice. What is the total distance that the player traveled? And what is the origin? So I suggest you pause this, record your answers on your sheet here, where you have access to the definitions of the terms. So hopefully you pause this so that you could reflect on it. I'm going to go over the answers. If you haven't paused it, please do so. So what do the stars represent? The stars represent the positions, right? The blue star is home plate. The red star is first base and the yellow star is second base. And we could pick any origin we want in order to define this, and we could give you a length and a direction from that origin. But those represent locations or positions. We don't have a frame of reference here by which we're making those, telling you where they are. We're just kind of marking the spots. What do the arrows represent? What do the arrows between these stars represent? Now, notice I'm saying, what does the arrow represent? So we can eliminate the distance because these arrows actually are telling us a direction. So we're looking at position or displacement, and these aren't super, this isn't a super great way of wording things. So the answer I'm looking for here is a displacement. We have a measurement, 90 feet. So from the blue star to the red star, my displacement is 90 feet, roughly northeast. From the red star to the yellow star, my displacement is 90 feet, roughly northwest. I'm going to show you a better example of displacement. This one isn't super great because we've moved our origin for that second arrow. Really, the true displacement would be from the blue star to the yellow star. That would be ideally what we'd be looking at, but that requires some algebra that some students may or may not have had. at this point using the Pythagorean theorem, etc. And so we're not going to work with that particular one. Certainly doable, but just a little bit beyond our scope. So let me show you an example of displacement that is a little better illustrated. Here we go. Let's look at this one. So I can get from this log cabin to the lake on one of two paths. Here's path one, this windy path that is they don't give us a measurement, or this longer, windier path, path two. And the length of path two would be the distance I traveled if I took that path. The length of path one would be the distance I traveled if I took path two. But my displacement, the straight line distance from that log cabin to that lake, is given as 5 kilometers, and our angle, our direction is 40 degrees. 40 degrees, we would say north of east. That's not something you have to worry about too much. We'll help you with those dimensions. Here's another example, right? Our distance traveled is this long, crazy path. Our displacement would be the length and direction of this lower arrow, okay? Here's one that's kind of similar to what we were working on. If I go from the tall building to the short building to the one-story building, then my displacement is 3.6 blocks at 56 degrees south of east, okay? But my total distance traveled would be 5 blocks. I go 2 blocks and then I go 3 blocks down, so a total of 5 blocks. If you're having any trouble with that, please let me know so that we can go over your questions. But hopefully these examples have helped make a little more sense out of the difference between distance and displacement. Then what is our total distance that the players travel? Well, 180 feet. We travel 90 feet and then another 90 feet, 180 feet. In this example, the origin is the blue star, or home base. All right, here's the last little bit that we got into today, and starting to talk about motion maps. So a motion map represents the position of an object at a set time interval. By looking at the spacing between the dots of the motion map, we can determine position, relative speed, and whether or not the object is changing speed. So as we look at this, notice that the dots for this image are getting further apart as it goes. It's a little hard to see towards the end, but they are slightly larger each time. So that means the car is changing speed. In fact, it's speeding up. If the separation were decreasing as we went along, then we would be slowing down. And if the spacing was constant, the same distance in between each of the dots, then we would be moving at constant speed. Now, some of these may have, we kind of got to get up to speed. So there may be a little bit in here that we're getting up to speed, but we can check on these other values. I don't know that I can, I can't pause it on this. We didn't get to this one. I can look at these values over here and see that they're getting a little bit further apart. All right, so here's kind of where we wrapped on our classes. We went over number 4. A motion map represents the position of an object at set intervals. By looking at the spacing or distance between the dots of motion on a motion map, we can determine the position, relative speed, and whether or not an object is changing speed. And then I asked students to do the quick practice, A and B. Notice one's on the bottom of the page and one's on the top of the next page. So the first one says, which object is traveling faster, object A or B, and what do you see that lets you know that? If you need to, pause the video and go back. I just talked about that spacing. On B, which object is moving at a constant speed? Which object is speeding up? Which object is slowing down? And how do you know? We're going to pick up here at this quick practice at the beginning of class tomorrow. All right, if you have questions, please let me know. Otherwise, that is it for this lesson.